think I'm going to push off discussion of homework problems until next week and try and push through something. 4 manifolds, 3 manifolds, try and the story sort of. It's a longish story, but I want to finish it. Okay, so we were talking about framings of knots. Let me back up just a little bit. And so we said this is the general setting, right? We have if K, that's what we call the image of an embedding of S1 for some B, embedding of S1 inside some n minus 1 dimensional manifold. All these minus ones are, sort of annoying, but that's because I want to remember that this is really coming from building an n-dimensional manifold attaching a K in, right? And then the question, we said that B extends to a capital Phi from Sk minus 1 across B n minus K, and if and only if the normal bundle of K is trivial. So one direction is obvious. If this extends, then you can take this as Sk extend, meaning, Sk minus 1 is sitting inside here as Sk minus 1 cross 0. And so one direction is obvious because this has trivial normal bundle, it's an embedding. This is an embedding. And then the other direction of the normal bundle is trivial, knowing that you can extend is the two-degree neighborhood theorem. Because the normal bundle, the point is the normal bundle trivial means the normal bundle is, or the unit disk bundle in the normal bundle is isomorphic to that, and therefore the two-degree neighborhood theorem tells you that the normal bundle being trivial will give you an embedding of this as a two-degree neighborhood. Okay? And then the question is, what about different extensions to this up to isotopy? And so, isotopy classes of extensions B, different ways to extend up to isotopy correspond are one-to-one correspondence with isotopy classes of trivializations. Knowing that a bundle is trivial doesn't mean there's only one way to trivialize it. And a trivialization is a particular isomorphism between this bundle and the trivial bundle, Sk minus 1 plus Rn minus K. And remember, trivialization, so another way to think about it is a trivialization is equal to n minus K linearly independent normal vector fields along K. So along every point on K, we have n minus K linearly independent vectors that are normal to it, which varies. Okay, so that's an n minus K frame. So such an isotopy class is called a framing. Framing, okay. Now we talked about framings of S0s and looked at 4 different cases of those, and then we specialize right away to the case where if K minus 1 equals 1 and n minus 1 equals 3, then we have frame knots. 3-manifold. Oh, and so the other thing is that you might remember that the example of the framed S0 inside a 1-manifold, and there were actually 4 different framings, whether you went like this, like this, like this, or like this, right? But actually, these two give the same manifold when you attach a handle. It's just the handle's flipped inside out, right? And so there's some issue that you always get, if you just take this definition, you always get 2 different framings that give you the same manifold, and they're related by some sort of consistent all across the board orientation flip. And I'm going to leave it to you to figure out exactly how to state that. We mod out by that right away, and don't consider those. We don't consider these to be different. Okay?
Even if you're going to attach 50 other handles later on and so on.
Yeah, because it's just, well, I mean, again, it's just up to attaching a handle. First, you just argue that when you attach one handle. It doesn't, I claim that when you attach a single handle, whether you attach a single handle according to this framing of S0 or this framing of S0, doesn't affect the diffeomorphism type of the coordism. Okay, so actually on the top is still diffeomorphic as well, and so therefore, you know, a later handle, you know, that it's just handle by handle. It just the whole coordism is broken up into elementary pieces in each handle. I don't know if that satisfactorily answers your question. And so, you know, the issue what comes up here where I say that a framing trivialization of a knot K, because this is a codimension 2 thing now, right? So the normal bundle is 2-dimensional. So this really is equal to 2 linearly independent normal vectors. But let's make the assumption, so convention, we're always working with, everything's oriented, and so this is, M. M is oriented, and K oriented. Let's call these normal vectors V1 and V2. Right, and the convention would then be that, so the convention is that the tangent direction to K, which is an oriented direction, followed by V1, followed by V2. I want this to be an oriented basis. Okay, so as I go around, this is just a, so here's my, this is just my curve. Here's the tangent vector, and then here's V1 and V2. And then that should follow the right-hand rule. Okay. If you make, my claim is if you flip that convention or require, say, that V2, V1, in that order be an oriented basis, you'll get another framing that gives you the same manifold in the same way. Okay? So some consistent flip of orientations, conventions all the way along doesn't change the manifold. And this is just a convenient convention because then, therefore, you really, up to isotopy, only need to specify V1. Only need to specify V1. Okay? So you just specify a single nowhere zero vector field along K, and that determines the framing. And then we said, well, identifying the normal bundle of K with a 2-bit neighborhood, then we see this, then V1 is a parallel copy of K, often called a push-off. So actually, it's a normal, the vector is not in the manifold, but if I push it down to the manifold using the exponential map, then then I look at its endpoint, that traces out a knot that's right next to K, and parallel copy of K on the boundary of the 2-bit neighborhood. And so one way to specify a framing then would be to draw your knot. That would be K, and then to specify the framing by drawing a parallel copy that twists around at some of these times. That might be an example of a frame knot. So this will be the push off. And then what we said, again, just to summarize, the upshot is what really counts is how many twists, but of course, how do you decide whether that this should count as 0 twists or 10 twists or what? It might look like it's 2 twists, right? But it turns out if you draw the knot in a different way, if you do an isotopy in R3 of this configuration of 2 curves, you draw the knot differently, you will get a different, it may end up looking like it twists differently. okay? And so measuring framings, we'll talk about how to do that shortly, but in general, it's a tricky thing. So what we say is that the framings, set of framings of K, is a Z-torser, which means, or an affine space for Z, which means a Z acts on it. And so we have to tell you what adding 1 is. So plus 1, yeah, that means you replace. So if I have a single framed knot and I'm going to change it to a new framing of the same knot, then if in some ball I see this, then I replace that with a right-handed twist. So that's supposed to twist, the red curve twists around it once, right, in that sense. And that's, so, a right twist. So plus 1, right twist.
Do you need to draw little arrows there to show the orientation of the...
Good question. So if you go the other way, it's also a right-handed twist. Okay, this is right, and that's right. So the red is twisting to the right around the white, and coming the other way, and then it's just okay. So another notation you'll sometimes see is, this is also sometimes denoted like this, box plus 1. This notation means inside that box there is one full right-handed twist. Okay?
So these you don't really have to specify a minus 1, right? Because you can
Minus 1 is, you
just like undo it.
yeah, you could undo
Because
it,
you could like artificially
create
and then undo it.
a plus, and we create, right.
Then you
But
get
but actually a minus 1 is a right-handed twist. Because plus 1 and a minus 1 in a row, do a right twist and then a left twist, you can isotop it and undo it. But let me just say a little bit more about why this is how you think about framings in general, right? So the point is, how do we compare what's really going on here? Why is it Z? How do you compare two framings and so on? How do you change a framing? So in general, right? So a framing of K, let's say, two framings of K differ by, so K, let's remember now what is this point. So this is, K is phi of Sk minus 1, and the framing normal bundle of K is then diffeomorphic isomorphic Sk minus 1 cross, well, I'll think of it as a bundle itself, R n minus K. Okay, when I think of it as a two-bit neighborhood, I should say a ball. When I think of it as a vector bundle, I should say R. Okay. So two framings of this would differ, well, at any point in the sphere, Sk minus 1, you have two different bases for R n minus K, so they differ by an element of GL of n minus K, right? So differ by a map, a smooth map, let's call it delta for difference, from Sk minus 1 into GL of n minus K. Okay, let's just change the basis matrix. So then you got one basis, you got another basis, at every point you have to change the basis matrix. And so if all you care about is then up to isotopy, then all you care about is the homotopy class of this map, right? So up to isotopy, we have to think a little bit about homotopy versus isotopy. If I change this map by a homotopy, that means just at every point on the sphere, I'm just moving the element of GL of n minus K by some amount, and that's going to isotop the framing around. In other words, you might be bothered isotopy, homotopy, but they're different issues here. So up to isotopy, we just care about sloppy about base points here, the equivalence class of delta in pi k minus 1. That's homotopy classes of maps of this k minus 1 sphere into GL of n minus K. to think carefully about base terms. So why is this z? What's going on here is pi 1, right, because k minus 1 is 1, and this is GL n minus k here is 2, because that's the codimension, right? N minus k is 2, so GL2 is, well, GL2 deformation retracts onto rotations. Right, we're already, this is two components, right? Actually, even when this is 0, it makes sense as well. In that case, when you have pi 0, you have the orientation issue. But anyway, this is z. It's just how many times you twist around. Okay, so that's really what's going on with this. And so if you so this, I mean, really, you can use some Gram-Schmidt orthonormalization process and always assume your frames are orthonormal, right? And then you can say this is really pi 1 of SO2, and that's just pi 1 of the circle. That's pi z. And so, for example, I think I said something wrong last time. I said there was some, I think I said when you have two spheres inside R4, you have some interesting framings. That's not true. When you have two spheres in 4 dimensions, you don't have interesting framings, but because you're still looking at codimension 2, pi 2 of S1 is 0, but interesting framings come up, for example, if you're looking at two spheres in 5 manifold, right? Then you have even we'll have 1 spheres in a 4 manifold. So if k minus 1 equals 1 and n minus 1 equals 4, then you're looking at pi 1 of SO3, and that's Z2, 2Z. And so now there are only 2 framings for a knot inside a 4 manifold. There are exactly 2 framings, not Z's worth of framings. But anyway, we're going to stick now to this. Case here. Any questions?
What are the homotopy groups of GL?
In general, I have no idea.
No idea. Is that-
I mean, there are tables and lists. I don't think they're all known. I mean, it's like I'm not at but lots of them are Z and Z2, and lots of them are 0. Okay, so now let's actually I'm going to push aside the issue still of how. I mean, there is a way. Let me say this. Issue that I want to do for a little bit, but if I'll say this right now. There's a special case of frame knots, which is relevant in many cases, which is that if you're looking at, again, n minus 1 equals 1, k minus 1 equals 1, n minus 1 equals 3, right? And then we've got k inside a 3 manifold. K is 1-dimensional, k is not. Then if the homology class of k is 0 in one of them, in terms of coefficients, this just means that k is the boundary of the surface. Okay? So i.e. k equals the boundary of some certain sigma of the surface. There's lots of little details I'm pushing in the rug. It's not entirely obvious that if you have a 1-dimensional submanifold of a 3-manifold that is homologically trivial. That just means it bounds a two chain, a simplicial 2-chain, right? It's not entirely clear that can be represented by a 2-dimensional submanifold, right? But that can be. But then what you can do is, so this is a surface in the manifold, a surface, an oriented surface. Oriented because it carries homology in itself, if you're doing over Z. Then you can measure framings of K as intersection number of push off with sigma. And I'll just show you this by an example. There's an example over there. So here's the surface of the trefoil knot bounds. It's the first surface you might think of is this surface. Okay, but that's not oriented.
We're in S3.
Or in S3 or R3. Okay, right. So the first point is this always happens if the three manifold is S3. Okay? Every knot is not homologous to S3. So this is bad because it's not oriented, so we don't like that. But there's another surface which is, if you've never seen this before, it takes a little bit of time to digest. But you draw, here's a little triangle in the middle, and then I'm going to draw something on the outside here. Now, if you're in S3, you can be happy and just say, well, that goes off to infinity. But you don't have to be in S3 actually to say that, because you can just imagine it's a big bubble that goes around the back. I just don't want to draw. So really, there's a bubble that goes around the back, and there's a sheet here and a lower sheet there. Okay, and then I've got a little half twisted band here. Half twisted band here. If you guys did a knot theory course, you would have said you would have seen cyclic surface construction. If you've never seen it, there's a nice algorithm as well to produce what's called a ciphered surface for a knot. And now suppose I wanted to draw a push-off that doesn't intersect this surface at all, right? I should come through here. Let's say I want to draw something that's 0. And here it's not intersecting the surface. Now if I wanted to come out here and still not intersect the surface, it's got to go under. And now I avoided intersecting the surface there, because I'm behind, because this is a half twist. And then I come here, if I want to avoid intersecting the surface here, I better go over. And then if I want to avoid intersecting the surface here, I better go under. And then I want to avoid here again, so I'll go over. Some things like this are better done in privacy or whatever. You can get the idea anyway, you can check it yourself. Go behind here. And then I gotta go over again. And that should actually be here. And I claim that I've woven around that surface and avoided intersecting it anywhere. And this actually is the best choice of something to call 0. Okay, even though it looks like it twists a lot, right? This one over there, well, if you imagine this one without any twist, let's say we can figure out what this is the following way. Okay. If I didn't have these twists at all, then when I come through here, I would be, imagine it's right here, okay? It's gonna go, and let's suppose I wanna get, here I need to get to under. So right here, it's gonna puncture through the surface once, okay? So there'd be one puncture here, it punctures through the surface once, and then I'd be behind. And now I wanna get, let's say I could stay above all the way through here, and then I need to get behind, so I'd puncture through the surface again. Ignore these for the moment. I'd come around, I'd be above, 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 and I have to puncture through the surface again. So I'd intersect that surface 3 times. Okay. Now let's think a little bit about sign. We should orient this, the way you orient the surface is so that you orient the knot one way or the other. Turns out it doesn't change things. If I not orient this surface, let me orient the surface this way. Then here's this little piece of surface, the boundary is oriented counterclockwise, which means by usual convention, this is the positive side of the surface. So a intersection between a surface and a curve, an oriented surface and a curve, is positive if the curve comes from from the negative side to the positive side. So if this has, a surface is oriented by its normal vector, so if that's up, then this would be a plus. It's going that way, it's a plus. So if I orient, so that means this is the positive side, that's the negative side. So out here, that's the negative side and that's the positive side. This curve, if it's oriented you orient the push-off pair in the same way you orient the knot, and then you come through along here, and then you punch through, which means you're going from negative region to positive region, because this is the negative side, that's the positive side, and that's a plus. And these are all pluses, and these are all pluses. Now, if we put in these, so these are all plus ones, counting the intersection. Now, let's see what happened here with this extra twist. I claim that extra twist because these are left-handed twists, should subtract 2. So right here, it was above the surface. It went behind, now it's coming, there's one point of intersection right here, where it pops from the positive side to the negative side. So that's going to be a -1. And there's another one right there, that's a -1. So I claim that when you sum all this up, this is framing +1. Relative to that, even though it looked like it had 2 twists. Now, for a little background reading on this, I highly recommend Rolfson, Knots, and Links, in which there are 10 different definitions of a linking number. Of which this is one of them. And what we've really done also is we've computed, so this measurement of the framing identifies an integer with a particular framing. And another way to say is what we've done is we've computed the framing is really can be thought of as the linking number of K with the push-off. The push-off, the framing really gives you the push-off, but to identify it as an integer, we use this thing called the linking number. There are all kinds of beautiful formulas for linking numbers. One of them can be computed in terms of the, there's integral formulas for the linking number and so on. It's a nice subject, but it's, I think more important for us to remember is that there's no well-defined linking number if you don't have that surface.
Are there nice general conditions for
I mean, besides just S1 and S, besides in this dimension, because this is the most general.
No, say in dimension. I mean, like, is there nice conditions on like homology of the 3 manifolds of the unity of cycle surfaces?
Homology is 0, that's all. I mean, it has to be the one-dimensional homology is 0. Otherwise, as long as the one-dimensional homology is not 0,
You just, like,
there's
wrap
always
around.
some circle that doesn't satisfy this condition, right? And you could attach a handle.
But
on
there's
that
not
circle.
some like H2 condition in those.
No. I mean, you could even if you have torsion in H1, which doesn't appear in H2, you could have H2 be 0 and torsion in H1, and then you could still attach a knot along
It's like
something.
arcing through
Yeah, right. Okay. So now let's remember that we're really trying to focus on building 4 manifolds. Okay? So that was all about how do you draw the attaching map for a 2-handle attached to a 2-handle in a 4 manifold, right? So that's what we call building 4 manifolds. Yeah, building 4 manifolds, what I really want is how do you give instructions for building 4 manifolds. Okay, so remember the 0 handle, you don't draw anything. Empty space is the boundary. Empty space is R3, which is R3 union infinity, which is S3, which is the boundary of the 0 handle. Then the 1 handles. Now, in principle, I should draw framed 0 spheres, right? But framed 0 spheres, well, we discussed, it's essentially the same issue that we saw in 0 spheres in R1, in 1 manifolds, where the same issue holds. If we're making the convention that everything's oriented, we just need to draw the points. But instead of drawing the points, let's draw balls. And so we draw balls mainly because it helps us to keep track of if I have something that's going to come into this ball and go over the 1 handle and out the other side, I'd like some way to keep track of how strands entering correspond to strands leaving. Okay? And the 2 handles are framed, we draw framed knots. Framed knots. and they may or may not go over the one handle, right? So we could have something like this. Actually, I'll draw a classic important example right now. That's right. Here's an example of an interesting frame knot. So there's a one handle first, and I'm going to draw a two handle that goes over it 3 times. Okay, so there's also a convention in these pictures that sort of there's no twisting as you go over this one handle. So this strand corresponds to this strand. Okay. So then I want to bring everything around here. Now these are 3 strands, but they're going to turn out to be the same one handle. So what I want to do is I want to put a crossing between 2 of these, and then I'll extend that, and then I'll put a little clasp here. Now I've just drawn the image of the attaching handle, and not the. I've just drawn the image of the circle. I haven't drawn the framing. Let me just say with blackboard framing. I don't know. I just choose an example. So I could blackboard framing remember means you push everything off. The normal vector is precisely the vector in the plane. Of course, then you have to say what happens over here, but the assumption is that it's invariant as you go over it. What's happening here? Remember, there's an integral cross S2 that you're going through there. And this is an important example because actually it's if I just take 0 handle, 1 handle, and 2 handle, this is a contractible 4-manifold that whose boundary is not 3-sphere. And so the reason it's contractible is that if you think about this one handle, this two handle, it goes over the one handle once in that direction. Now it turns around and goes back over the one handle this way, and then it goes over it again. And so there's an issue that we'll come up with later, but there's a way to sort of compute what's going on with homology and so on, and see that the fact that it goes over, it sort of almost cancels this one handle in some sense, because if you could just undo this clasp, right? And then if suppose you could undo this clasp, then this would be this part you could pull off and pull over the one handle and make it not go over the one handle all, and it would just be like a 2 handle going over the one handle once. That would be the convertible roof, which would collapse, and this would be the 4-ball. This little clasp is what prevents it from being 4-ball, that's called the Maser manifold. Barry Maser, I guess, now does number theory, but here's the point now. This thing, its boundary is not S3. And because its boundary is not S3, you cannot cap it off with a 4-ball. Okay? Now you might, with a 4-handle. And so, the question now is, what about 3 handles and 4 handles? And, well, what do you need to do? In order to know whether you can cap things off with 3 handles and 4 handles, you need to recognize what 3 manifolds you've achieved after attaching some number of 1 handles and 2 handles. Okay? So you need to understand the 3 manifold you get after attaching 2 handles. And we'll remember surgery. Surgery is how a manifold changes, how the boundary of the manifold changes when you attach the manifold. So actually, let me just give you your exercise. So first, for the 1 handles, prove that the boundary of something made with just a bunch of 1 handles. I'll just give you. I'll do 2 for this. So what is this? This is a 4 manifold, right? This is a four manifold with zero handle and two one handles attached. Prove that the boundary of that four manifold is equal to S1 cross S2, the next sum, S1 cross S2. I'm going to give you another homework problem about S1 cross S2, so it occurs routinely. Of course, once you've done, there's two of them, it's two S1 cross S2s. If there's three, then it's three S1 cross S2s. So figure out a way to explain why that's true. And if you then take that as given, then one handles don't pose much of a problem to understanding, and the two handles are where the subtlety lies. And now I'm going to suppress the one handles and just think about the two handles. So now I have to understand surgery. Two handle attachment maps. So remember now, when we attach a two handle, we attach a two handle along an S1 cross B2, right? And that's the attaching map, that's the attaching region for the two handle. We cover that up, it ends up being in the interior of the four manifold, and we have a new piece of boundary, which is the complementary, the free region. The new boundary, this is removed from the boundary, and replaced with B2 cross S1. And of course, if you're replacing it, they better have the same boundary. And so the point is that the boundary of S1 cross B2 equals the boundary of B2 cross S1. And so this is the most famous type of surgery. You have some solid torus inside the three manifold. Okay, so here's where it gets weird and hard to visualize. You have a solid torus, which you've identified with. Remember, the framing is important now, because you've identified this solid torus with S1 cross B2. This is your S1 cross B2. You remove it, so this is sitting inside the three manifold. Okay? Now you take M minus S1 cross B2. And when I remove something, I'm really just removing the interior or removing the whole thing, taking the closure, either way. So now the boundary of this, well, I'm going to say it's equal to S1 cross S1. But remember, S1 cross S1 has many diffeomorphisms to itself that can be different. So in order to remember how it's equal to S1 cross S1, let's remember which this S1 factor is the original around S1, and this S1 factor is what bounded with B2, okay? So we will call these, this is going to be called meridian, and this is going to be called longitude. Because meridian equals bounds, the one that bounds the disk. This is the one that bounds the disk before you do anything. Okay, so here's this particular example. This is the meridian. Now, but we have to be a little careful here. There are many different ways. This is basically a push-off of S1 cross 0. The longitude is push-off of S1 cross 0, mu, or assuming things I didn't say, I often use mu for meridian and lambda for longitude. Okay? And so now I need to draw a longitude here. And I could, depending on what framing I chose, that push-off will look different. It might wind some number of ways around. So this might be like this. Okay. And so lambda, in other words, what I'm drawing really is S1 cross the point. Of course, there are many, the whole boundary is foliated by that. And so, now and then you replace, you glue B2 cross S1 back in, And the key thing is that you glue it in so that this becomes the boundary of that factor. This is bounded by that factor, so this is glued along that. And that's what I cannot draw a picture of. I'm supposed to draw a solid torus, E2 rough S1, and the boundary of the disk now is supposed to be blue, and red is supposed to be meridian. Sorry. This is, I'm going to glue this in so that the blue stuff corresponds to the blue stuff there, and the red stuff corresponds to the red stuff there. And that's going to obviously change the manifold in a highly non-trivial way. And that's called surgery on a free manifold, and you need to specify a frame knot to do it, and you want to try to stare at examples of these to get an intuition. Probably the beginning is the first example to look at. Here, first examples. So now I'm describing a three manifold or a four manifold. Okay? What does this picture mean? This means I attach, as a four manifold, this means take a zero handle, now attach a two handle to it with framing zero. Okay? So that means, so as a four manifold, this is equal to a zero handle, two handle, and then the zero means that I should use the push-off that doesn't intersect a cyclic surface at all.
Because
Okay?
we have no one handles where in us.
Because I have no one handle, I just have a single zero handle. This two handle doesn't go over any one handles. So therefore, this two handles will attach along a knot in the boundary of a ball. Therefore, I want a knot in S3. Therefore, what I have, it's null homologous, so I can find a surface that it bounds. I might as well take this surface here. I take that surface there, and then the zero means that I'm taking a parallel push-off that is disjoint from that surface. Okay? And so that now I attach a two handle, like I use this parallel push-off to construct a embedding of S1 cross B2 into here. And then you narrow it. And now I attach a four-dimensional two-handle along this knot, and claim, so this is a four manifold. The next exercise we should do is actually starting to sound familiar. Now so zeros always look like unknots is the problem.
You will orientate.
Huh?
You give like the, you can give the unknotable orientation.
Oh, so I know it's not a zero.
Yeah.
Anyway, that's the number zero, this is not. And so the boundary of this four manifold is equal to S1 cross S2. Okay, and then, but now the other one is, if I take, let me do plus one. Okay. So plus one means I'm supposed to draw the push-off that goes around, and then if I orient the knot this way, right, then this surface, this is the positive side, I'm supposed to draw a push-off that intersects it positively once, means come through from below and come from the negative side and out, so I want to draw this. So that's my parallel push-off. Okay. This again is a zero handle union two handle. But now I've used a different framing, and the exercise here is to show that the boundary of this plus one is equal to S3. Again, so actually you do the surgery and get back to S3. So remember, again, all this data means you thicken it up to make a trivialization of, to make, you use this trivialization of the normal bundle of the tubular neighborhood theorem to get a tubular neighborhood, identify with S1 cross B2, you attach a handle on this way.
So really here, the blue corresponds to
Yeah, blue.
the
lost
push-offs
meaning
are
here.
like the longitudes, right? Those are-
Push-offs are the longitude, that shouldn't use blue over there, sorry. Okay, so, but here's another way to think about surgery though. You have something that is a meridian before surgery. You have some curve on the tubular neighborhood, on the boundary of the tubular neighborhood, which bounds a disk on the inside. Okay, that uniquely determines mu up to isotope. After you do surgery, the longitude becomes the meridian. The longitude ends up bounding a disk. And so after surgery, this will be the thing that bounds the disk, and this won't. And so sometimes you want to say this is the meridian before, and this is the meridian after surgery. And when you just draw a solid torus without framing it, okay, the meridian is totally specified by the fact that it bounds a disk. But the longitude depends upon your framing, which total longitude you choose, and that determines the surgery you get. So this will be called +1 surgery on an unknot, and that gives us 3. You can also, you're free to look this stuff up in Rolfson, Knots and Links, or any other Gomford Stipchits, or any other, or Wikipedia, or whatever. There's probably nice explanations for why these are true. Actually, same thing is true for -1. So boundary of -1 equals 3. I think maybe we should talk about this early next week so we can kind of make it pretty clean. So try and think about these examples even if you haven't thought about other homework yet. But it's nice to, it's much better if you struggle with them yourself than if you see me draw a bunch of pictures on the board that you haven't thought about. However, here's the key thing about this though. If you believe this is S3, then what can we attach? A 4 handle, right? We can cap this off. So I could also say, so now I could say +1 union of 4 handle, and this is a see, if I just draw this without saying union 4 handle, it's unclear whether I'm talking about a closed 4 manifold or something with boundaries. So saying union 4 handle just reminds you I'm going to cap it off in the end.
Also,
But in order to write,
the other thing has boundary S3.
yeah, if I say union 4 handle, I can't do that unless this thing has boundary S3. This thing could conceive, I could have some way of doing things where they have disconnected boundary, but that's another story. We need 3 handles to make that happen. Notice I don't have any 3 handles now. Notice I'm sort of avoiding the issue of 3 handles. So this is then a 4 manifold. It turns out that this is diffeomorphic too. This is not exercise. I'll try and explain this more carefully. This is CP2. With -1, turns out if you just reverse all orientations, that will change all your framings. So this is sort of something to keep in mind as well. This is diffeomorphic with CP2 with a reversed orientation. Let me.
You might have guessed that was S4.
You might have guessed it was, no, here's why you wouldn't guess it's S4. Okay. It has a handle decomposition. Here's why you would guess it's CP2. It has a handle decomposition with a 0 handle, a 2 handle, and a 4 handle.
Okay. If you know something about homology.
So well, let's not even be so sophisticated as homology, let's just think, so let's think about a cell decomposition. So 0 handle, in terms of like up to cells, is just like a point. Okay? I got a point, and then I attach a sphere to it, and then I cap off with something, right? So it's not going to have right. Yeah, but then you can think about cellular homology or something. There's some two-dimensional, non-trivial two-dimensional homology that's not killing any one-dimensional homology or killed by any three-dimensional homology. There's no 3-cell to kill that 2-cell. Okay. So I mean, we'll try to do
shouldn't be S4.
So it shouldn't be S4. It turns out it's got non-trivial homology. And then CP2 has exactly that right kind of homology. So does CP2 bar, but that's not a proof that it really is.
I'm confused by the fact that both of those had they're bound to being the same thing, S3. And you said there's only one way to attach the four handles. So how can we get different manifolds?
One's plus one, I mean, but what's that, the two handle is different inside. Okay,
Well, those are diffeomorphic as manifolds. So
their
CP2 is-
orientation reversing different.
Sure.
Right. So, let me illuminate something in the remaining 0 minutes, okay? And talk about more. So here's something you can see inside this format in this picture. You can see, so there's the core of the two handle is a disk, right? The two handle is D2 cross D2. I take D2 cross 0, it comes down, and then it's attached right along this circle. Okay. Now, this circle bounds a disk, right? Which if I like to make things smooth, I can push a little bit into it bounds a disk inside S3 and push it into the four ball, into the zero handle a little bit. So there's these two disks fit together to make a sphere. Okay. Now let's think about, so there's an embedded sphere inside this four manifold. Okay. Now, if I push that sphere, I want to push that sphere off itself just a little bit. So I push that sphere off itself, push the disk off itself in the handle. It means I take a parallel copy of the handle. It's D2 cross D2. I take got D2 cross 0 and D2 cross a point. That'll look like the image of, that'll look like precisely this push off here, right? So that'll, I mean, I'll have to say this next time, really, but it's just food for thought. That will then, that will not intersect, I've got a sphere and it pushes itself off in the northern hemisphere at least, and part of the handle doesn't intersect itself. And then I try to push itself off on the southern hemisphere, which is inside the sphere, and I can make it not intersect itself. But then go from one to the other, I have this little kink I have to get rid of, and I'll force a single intersection point. And this ends up being a sphere that has, which if I push it off itself, has to intersect itself at one point. And that'll be a positive intersection. This is, for those who know, this thing has, that sort of almost characterizes the complex projective space, that it has this sphere inside it that intersects itself once. But we'll do that later.